Hello, welcome to today's mechanics tutorial video where I'm going to be showing you how to do calculations involving forces, specifically calculations that come from looking at Newton's second law. So, what do we need to know? Well, I've already given the game away in the title of the video. It's a formula, and the formula states that the force acting on an object is equal to the mass of that object times by the acceleration that object experiences. And that's more simply remembered by the formula F equals ma, which is of course just taking the letters that begin all those words to make it a bit easier to remember. You should also be aware of the units each of these quantities are represented in, so it's worth mentioning that force is usually measured in newtons, mass is usually measured in kilograms, and acceleration is usually measured in meters per second squared, and these are what are known as standard units for these sort of calculations. Something else I probably should mention though is that this is effectively what we call Newton's second law. Technically it isn't directly, because Newton's second law is basically written as a more formal definition in words, but it's basically establishing this relationship between force, mass and acceleration and how they have this relationship with each other. So there we go. With that said, let's start putting into practice, and one of the most simple examples I can give you for showing this equation in action is when it comes to the weight force. I have already mentioned in a previous video that weight is a force caused by the acceleration due to gravity acting on an object. But if weight is a force, that means it must be measured in newtons, which is a bit controversial, because if you think about day-to-day language, often when we describe weight, people will say something weighs, I don't know, let's say 2 kilograms. They are actually technically not talking about the weight. They're technically talking about the mass of an object, because that is the quantity that's measured in kilograms rather than weight. However, I can understand where this confusion comes from, and you'll see what I mean when we look at the equation that helps us calculate what weight is. And the calculation for that all comes from this equation, F equals ma, because the force of weight is calculated by doing the mass of the object times by the acceleration due to gravity. And of course, the acceleration due to gravity on Earth is what we call the constant g. Now in Maths A-level we take g to be 9.8, whereas in some other qualifications they might use a greater accuracy than that, and that is fine, but for our qualification that we're looking at, we use specifically g equals 9.8 rather than 9.81 or whatever else you might hear. And ultimately, due to this equation, I can understand why the words weight and mass have been confused over time, which is because of the fact that g remains relatively constant on Earth, so therefore that means weight and mass on Earth are generally directly linked by this factor of 9.8, almost all the time, and so therefore there's roughly just a single order of magnitude of difference between them. So now that we know this is how weight is calculated, let's put it into practice. So we have a couple of quick examples. In part A, we need to find the weight of an object that's got a mass of 6 kilograms. So therefore, W, the weight, will equal the mass of the object times by the acceleration due to gravity, G, so in other words, 6 times by 9.8, and therefore you can work out what that will be, 58.8. There you go. So that's the first question done. Obviously the answer would be in newtons because we're finding the weight force. On to part B. Ultimately this time we know the weight is 4. We don't know the mass, let's just call it m. And then we know the acceleration due to gravity is g. So therefore we know, rearranging this equation, that the mass is equal to 4 divided by g, which in other words is 4 divided by 9.8 for Maths A-level. And you just got to type that into your calculator and work out what it will be, which is 0.408, etc, etc. But it's worth mentioning, because we're only using g to 2 significant figures, we should technically round our answer to only 2 significant figures, so that we are not extrapolating the accuracy. So that's an example how F equals ma can be used on a small scale to work out what's going on with forces. However, this isn't really a true reflection of how we mostly use F equals ma, which is instead of focusing on just a single force and how that affects an object, we're instead more interested in how a whole system of forces combine together to affect an object. So therefore we're going to need to make a few adjustments to the idea we established already. You see, when we say force equals mass times acceleration, or F equals ma, it's kind of a bit of a misnomer because it's implying that we're only talking about one force, when in reality the F in F equals ma is referring to the net result of a whole combination of forces. What's the overall effect of having all those forces acting together? And that is what's linked to the mass and acceleration that an object is experiencing. But how can we work out what happens when we do combine several forces? Well, it's all to do with something we did mention in a previous video, which is this idea of positive direction. You, when approaching a question, if the question hasn't already done it for you, have to decide for yourself what you're going to define as the positive direction. This is important because it then informs what you do in the calculations. Any forces that are going in the positive direction will be added as part of the combining process, whereas any forces that are going in the opposite direction to the positive direction will be subtracted instead. Adding and subtracting the forces in this way is what then leads to you being able to know what the overall effect of that combination of forces is, which then allows you to place it in this F equals ma structure. However, it's worth mentioning that it's not just forces that are affected by the choice of positive direction, it's also acceleration. And that takes the form of basically looking at the sign in front of acceleration. If it's a plus, then it means the acceleration is going in the direction of your positive direction, whereas if you have a negative acceleration, it means it's going in the opposite direction to that. So therefore, that's something important to consider too. So let's put this idea into practice. We've got an initial example here, and the question says all the forces that are acting on a box of mass 7 kilograms are shown by the diagram. In many ways, this is a bit of a weird example in the fact that they've given us a force diagram already with all of the forces that we need on it, because normally we have to consider for ourselves extra forces that we know just from the environment should also be there, things such as weight or sometimes a normal reaction force and things like that. But to make this example nice and neat and quick so that I can just demonstrate how the F equals ma part of it works, I've simplified and just said all the forces we need to care about are already on the diagram. So we need to find the magnitude of acceleration. How are we going to do that? F equals ma. But what we need to do before we launch into that is first decide our positive direction. It doesn't matter which one you choose in terms of the final answer, it just changes how you're going to get there and how your working will look. It's important that you then notate this for the person who's reading your work, like an examiner, so they understand what's going on. So the way you notate what your positive direction is you do a capital R, you do an open bracket, and then the simple way of doing it is just to literally draw an arrow in the direction you're calling your positive direction. So as I said, to the right, therefore I'm doing an arrow to the right, close the brackets, and then put a colon. Putting that colon is important because it shows that this notation isn't part of the equation itself, it's not a variable we're actually having to calculate the value of, it's just a preliminary bit of information that informs how the equation should be interpreted. So now we can get on with F equals ma. So the first thing we're going to do is we're going to look at the F part of F equals ma, but reminding ourselves that the F is not just a single force, it's the combination of all the forces. So any forces that are going in our positive direction, such as the 4 which is going to the right, the 1 which is also going to the right, and the 7 which is also going to the right, will all be added together. And any forces that are going in the opposite direction to our positive direction, which would be to the left, would be subtracted. So we're taking away 6 and we're taking away 16.5. Once you have considered all the necessary forces involved in the situation, you're then finally done with the F part of F equals ma, so we can write equals, and then we can move on to the ma part. The m is 7 kilograms, so we write 7, and then we're timesing by the acceleration, but we don't know the acceleration. That's kind of the whole point. So I'm just going to write a. So now we've just got to solve this equation. So if we do that, the left-hand side will just become minus 10.5. and therefore solving it we get A is equal to minus 1.5 meters per second squared. But now we've got one more thing to do. As I said, the positive direction doesn't really affect the final answer, but it does affect how you interpret your working to reach that final answer. So, as we can see, we've got a minus sign in our answer. However, the question is just asking for the magnitude of the acceleration. The word magnitude means size, and that minus symbol is just to do with the direction of it, so it has no bearing on the size of the acceleration. The magnitude of the acceleration is just going to be 1.5 without the minus sign. So therefore the answer is just 1.5 meters per second squared. The reason the minus is important though is when we come to part B, because they now want us to decide what direction this acceleration must have been happening in, and this is where we need to interpret that minus sign. Because we got a minus sign, that's telling us the acceleration was going in the negative direction, in other words, the opposite direction to the positive direction. As we defined our positive direction to be going to the right, therefore the negative direction is going to the left. So therefore the acceleration is going to the left. Okay, that's our first example done. However, as I pointed out, this question was a bit of a weird one, just because the way it was given to us is not the format you're likely to be asked a question in an exam. I completely ignored forces like weight, and also because it's unusual because they supposedly had given us a force diagram with all the forces on it, and they had stated that in the question. So, to give a more realistic view of what sort of question you get asked in the exam, you're often usually given a wordy scenario and you have to interpret that yourself to work out what's going on. However, I therefore should give you some reminders of some advice that I've given you in some previous videos. Things such as when you're reading a wordy question, it's always a good idea to start by just doing a quick read through of the question just to get your head around what the situation is. Don't try and even deal with any of the calculations initially, just try and get your head around what's the physical scenario that's actually going on, because then you can start to think intuitively about what you're expecting to have happen and visualize it, all that sort of stuff. You should then do a second read through where you approach it in a more steady, thorough manner, extracting all the key information given to you in the question and putting it in a more summarized, easy to use format. You can do that by drawing things such as force diagrams, because that helps give you the necessary information you need in a nice, succinct manner. This stage of things is stuff that often isn't getting marked, but it is a good idea to do, and in fact students who often are lazy and can't be bothered to do this sort of stuff are the ones who make silly mistakes, miss forces out, etc, etc. So it's a good idea to do. Then once you've done that, you decide the positive direction and do the F equals ma calculation as before, because you've now simplified the question so it's in a format where it's quick to do that, just like in the previous example. So let's take a look at an example where we've got to do that, and here we go. At this point, you may even choose to pause the video to give yourself a chance to read through the question yourself fully, but what I would say is, in line with what I said about doing an initial quick read through of the question, all I'd be bothered with at the beginning is getting my head around what's going on, which is, after a quick read through, realizing that they've got this winch with a string attached to it that's lowering a box. And then because this is lowering the box too slowly, somebody else is then going along and pushing down on the box as well. I might even be tempted to do a diagram similar to what I've just done here, just to help me visualize what's going on, even though this is not what you would call an actual force diagram. And after getting our head around what the scenario is that's going on, we can then start our second read through where we're now going to extract all the key information so that it's all written down in a nice summarized way on our page, so that we're not having to repeatedly scan through all the words again when we're already midway through a calculation, because that's not fun to do. So therefore we start reading it and it mentions a box. So you know what, I'm going to draw a box because we're going to do a force diagram for our object. And okay, the object was a box this time, so it makes sense to draw a box for the force diagram. But you might remember from my force diagrams video, even if it was a more complicated object, I'd still represent it by a box when it comes to the force diagram to make it quicker to draw. It's got a mass of 10 kilograms, and that's something I can notate on the force diagram by writing it inside the box. And then immediately before I'm even reading any further, I already know if the object has a mass, it should have a weight if it's on Earth, because acceleration due to gravity will act on the mass. So therefore we're going to have the weight going down. Now I could at this stage just label that with the word weight or W or something like that, but earlier in this video we already showed you how you could start calculating weight. It's always just going to be the mass times by the acceleration due to gravity. For the moment I'll just write 10g, and that's something I recommend doing in the exams as well. You can worry about calculating what that is as a number later, not that it's a particularly difficult one in this case, but for the moment it's always a good idea just to be writing this down, just so you have something notated down and a rough structure of what you're going to need to do to calculate it already written down, just makes life easier. Okay, reading on, we can see the object is attached to a string. It's also attached to the winch, but not directly. It's indirectly attached to the winch by the string, but therefore I'm not going to care about the winch, because in my previous force diagrams video I mentioned you're only caring about the things that are directly affecting your object. So therefore we're going to deal with the string, and as the object is hanging freely, that means the string is attached from above, and therefore that's also important because it means the string is pulling upwards on the object. So therefore we're going to have a force going upwards of tension, which I'm going to represent with the letter T. Also, as it's hanging freely, that means we also know it's not coming into contact with the ground. That's important because it means we're not going to have a normal reaction force in this question, because that'll only happen if a solid object comes into contact with another solid object. We've also been told that the person's trying to lower the box, however that doesn't give us any new information yet for the force diagram. However, then later it tells us that the person is pushing down on the box with a force of 30 newtons. So therefore we need another downwards force, but this time of 30 newtons size. I'm just going to put 30 rather than 30n because you can assume that all the forces are in newtons if you're doing a force diagram properly anyway. We're then told that the box is being lowered with an acceleration of 2 meters per second squared, which is implying the object's accelerating downwards, and we can notate that on our diagram as well, but the way you do it is not by doing an arrow connected to the box, because that's reserved only for forces, so instead we do an arrow that's parallel to the box, pointing in the direction of acceleration, and also doing it as a double arrow to make it extra clear it's definitely not a force arrow. And we can write that number of 2 meters per second squared on there. Cool. We need to find the tension provided by the string, which makes sense. Once again, if we hadn't realized even from earlier that there would be tension involved, that would give us the second clue and reminder in case we'd forgotten about it that we needed to include it. And on that note, it's worth once again reiterating that we don't need to include a normal reaction force on our diagram, and actually that's something to watch out for, because things like weight and normal reaction are forces that the words aren't often going to mention directly, so you need to know just by thinking about the situation itself whether you need to include them or not. So that's something worth bearing in mind. Okay, now with all that effort out of the way, which some people might find a bit frustrating because we haven't really got into actually trying to solve the question yet, but doing this does pay dividends, because now if we want to actually do the calculations we need, they're going to be really quick. We just need to decide a positive direction. I'm going to decide to make downwards the positive direction this time, and therefore looking at our forces, we've got 10g going down, so therefore that would be a positive force for my positive direction. We've got the 30 newtons going down, so that would also be a positive value, and then we've also got tension, but that's going up, which is the opposite direction to the positive direction, so we're going to subtract it. Then that's going to equal, as we've now considered all the forces, we can move on to the mass times the acceleration. The mass was 10, and the acceleration also has to abide by the positive direction. Luckily, as the acceleration is going in the positive direction, therefore it's just going to be 10 times by positive 2, but it's worth pointing out that if my acceleration had been going up, then I would have had to write it as minus 2 when plugging into this calculation. Cool, and all we got to do is now solve this equation. Now I can start doing the calculations. 10g is just 98, plus 30, minus t equals 20, and of course this is all very easy to solve. Move the t over to the other side, take away the 20, and basically tension is equal to 108 newtons. So the answer is the tension is 108 newtons. Cool, that's the final answer done, and therefore we've got nothing more to say, and that will do us for today's video. However, there are still some things I'm going to need to tell you about with f equals ma. There's still more layers and extra details to add in, so do stay tuned for some future videos on this topic. You can look at those videos along with any other videos on the mechanics content that I've created by looking at the playlists which are linked on the screen right now. Have a look and I'll see you in a future video. Goodbye!